Hi, this is lesson 3-6, residuals and causation. So in our last lesson, we talked about line and best fit and linear regression. So for the warm-up, I would like you to open up your Desmos calculator and see if you can find the line and best fit for the given data. When you're done that, estimate the value of y when x equals 19. There is a Desmos link to the calculator in the resource folder, and there's also directions in yesterday's folder. All right. So let's go over this. So if you open up your Desmos calculator, I'm going to go ahead and grab my calculator. There it is. Okay, if you remember from our directions that are in yesterday's folder, to add a table, you have to hit the plus sign in table. And we're going to go ahead and enter in our x values. All right, and then my y values, I need to make sure they line up as well. Okay, so if I'm taking a look at my graph, I can't see my points because they go beyond where my graph is right now. So if I want to change my window, I'm going to hit the wrench button and I'm going to adjust my x and my y values. This is my domain and this is my range. So looking at my values, my x's go from 12 to 20. So I'm going to go a little above and a little below. I'm going to say I'm going to go from 10 to 25. Okay, that on my x's. My y values go from 35 to 48. So I'm going to go from 30 to 50. Now you can choose any numbers you want. I typically go a little above and a little below, just that way I can see all around my points. Okay, from looking at this, I can tell that it has a positive association or positive correlation because it increases from left to right. Okay, if I want to find my line of best fit, I have to come in here and I have to type y1, and then that squiggly, mx1 plus b. And then it gives me all of the information that I need. Here's my slope, my y-intercept, so I'm able to write my equation. And then it also gives me my R value, or my correlation coefficient. So let's go ahead and transfer this data to the other page. Okay, so looking at this, my equation, I can either write it in slope-intercept form or function notation. I'm going to do slope-intercept form for this one. So y equals, my m value, my slope is 1.55. And my intercept is 16.6. So this tells me that my slope is 1.55, my intercept is 16.6. Now it doesn't ask us in this problem, but our R value is 0.9943. As you can tell, that number is really close to positive 1. So that means that this has a strong positive correlation. Now that I have my equation, now I can solve for when x equals 19. So I'm going to go ahead and substitute 19 every time I see an x. All right, since it's all on the right-hand side, we can go ahead and put it in our calculator and see what we get. And I got 46.05. All right, so if we're looking at this, when x equals 19, 19 is not in my x values, but it would be somewhere in between here. We would have 19. So does it make sense that roughly 46 would fit in between 44 and 48? Yes, it's right on trend. So I know that that is an accurate or an appropriate estimate for that value. Okay, in today's lesson for 3-6, this is a continuation of yesterday's lesson. We did some of these things already. The new material is causation and residuals, but we are going to talk a little bit more about extrapolation and interpolation. But the other ones that are not highlighted are covered in our last video. So if you need a refresher, you need to go back to that video and check it out. All right, so today we do have guided notes. I want to show you what they look like. Our guided notes are in the folder. I made it where you can click and you can type in the definitions. When it comes to the graphs, just like in our test, you can double click them. It'll open up the drawing panel. You can add your points and then save it and they'll appear on there. Okay, some more definitions and writing. When you get down to the images, this one has a table. If you double click, you should be able to go into the text boxes and edit those as well and save it. That also goes for the definitions down here with text boxes. Just double click the picture and you should be able to add it in. And I also gave you space at the end. If you would like any additional notes that you want to have on here, feel free to add those to the end of your notes. Okay, this I do not need to collect, but I want to make it available to you. All right, our first definition is residual. And residual is the difference between the y value of a data point and the predicted value from the line of best fit. So if you remember when we talked about line of best fit, they are a prediction of what the trend line would be. Okay, they're not actual values. Some of them go through points, some of them don't. If you look at the one from the warm-up, this one didn't go through any of our points. They're close, but it didn't go through any of our points. So that's our prediction that we use for trends. Okay, so to calculate this is an easy way to remember it. For the residual, you take the actual y value, like the real value, minus your predicted value that you get from the line of best fit. When you do that subtraction, whatever value you get is called the residual. So basically what we're trying to figure out is how far off are the real numbers to our predicted numbers. Okay, and then we're going to figure out what that does for us in a little bit. So for example, this one we have our trend line, and you can see it's in blue. The red dots represent the actual y values. And the green, there's only 2 of them that are actually on there that they show, but there are more along this line, are our predicted ones from our line of best fit. Okay, this is called a residual plot, and this is how we record what the residuals are. So when we're doing this, we need to look at our actual value minus our predicted values. And we're going to come up with a decimal or a whole number that we're going to be able to plot on here. This one, we're going to tell, is it above our actual value or below our actual value? How much above or below? Okay, so if we look at our first predicted point, we have this predicted point right here. Looks to be about 1.5. And my actual value is 2. 2 minus 1.5, that means I'm about half of a point off. So I'm half a point, my predicted is half a point, really my actual value is half a point above this one, because it was a positive 1/2, actual minus the predicted. So I'm gonna go to where x equals 2, and I'm going to go to half a point above, and I'm going to put a dot. Okay, because this is my residual, like my line of best fit. I'm half a point above that. All right, this one here, when x equals 3, here's my predicted. Okay, so I'd say we can estimate that to be about 3.5 maybe. So if I take my actual, which is 4 minus 3.5, I again get about half of a point distance. It's positive 1/2. So I'm going to go to where x equals 3. I'm going to again go to positive 1/2. Okay, when we get x equals 4, this is the one of the points that are listed. So our actual is 3, and our predicted is 5. 3 minus 5 gives me -2. So when my x value is 4, my residual is -2. Okay, let's see if we can do the same thing for 5. Let's see, when we get to 5, yeah, I'd say roughly, if we're estimating, it's about 6.5. Okay, but there's no points there, so we really can't do anything with that one. So we're going to go to when x equals 6. All right, so my actual for this one, I have 2 of them on this line, but I can do one at a time. This actual one is 6.5. My real one is 8. So 6.5 minus 8, so that means I'm about 1.5 below, because it's going to be a -1.5. So I'm going to go -1.5, put a dot. And then I have another one that's also when x equals 6. So this one would not be a function. It would fail that vertical line test. My actual is 10. My predicted is 8. 10 minus 8 is 2 over. So I'm going to go to 2 over, and I'm going to put a dot. Okay, so this would be what the residual plot would look like for those 5 points that we have on this chart. We're comparing the actual value to the residual value. Now, our goal is to figure out if this is a good fit or not. In order to be a good fit, we want all of our dots to be as close to the x-axis as possible. So really, looking at this line of best fit is not a good fit because our points are kind of scattered a little bit, but they're not as close to the x-axis as we would probably like them to be. Okay? So what does it mean when you have a curve pattern in your residual plot? Okay, so you do have these on your notes, and you can write this next to it. This means your scatter plot is non-linear. So remember, linear means a straight line. So if you have a curve pattern like this, your scatter plot is non-linear. What does it mean when the points on the residual plot appear to be scattered at random with no visible patterns? They're kind of all over the place. Well, first off, we know, again, all of our points are far away from our x-axis, far away from 0. So this is not a good fit. But we also know it is linear. Okay, so linear functions are kind of more scattered, but because they are not all really, really close to the x-axis, it's not a good fit. They're just too far away from what we want. All right, so I want to show you a real-life example of when we can figure out what the predicted values are and what the residual values are. Student enrollment at Blue Sky Flight School over 8 years is shown. The owner used linear regression to determine the line of best fit. The equation for the line of best fit is y equals negative 35x plus 1,208. Well, how does this linear model fit the data? So the first thing we need to do is evaluate the equation for each x value to find the predicted values. So I'm going to show you the first one, and then you can pause your video. So if I take my calculator, I'm just going to use a TI-84. You could use your Desmos calculator or a scientific calculator. So what we're going to do is we are going to plug in 0 or our x values into our equation and see what our predicted y values are. So we're not looking at this number of students, okay? This is the actual. We're trying to find our predicted using our line of best fit. So my first x value is 0. So if I put 0 in there, I can probably tell this one without using the calculator. So negative 35 times 0 is 0 plus 1,208. So I can say that I have a predicted value of 1,208. All right, let's see if I might even have that hidden right behind there. Let's say, whoops. Yep, I do. All right. Now I'm going to take my next one, which is 1. Negative 35 times 1 is negative 35. So what's negative 35 plus 1,208? I get 1,173. So 1,173. All right, go ahead and pause your video. I would like you to substitute 2 through 7 into our equation and tell me what are my other predicted values. All right, so if you substitute 2 in, you get 1,138. 3 is 1,103. And then here are your other ones. So double check and make sure you have the same predicted values straight from our line of best fit. Okay, so we want to find the residuals. Remember, the residuals are the actual value, so the number of students they had, minus our predicted values. So for this first one, again, I'm going to grab my calculator. We're going to take 1,235. And we're going to take away 1,208 and see what the difference is. So this time, my prediction was 27 away from the actual, okay? So it was 27 on the positive side, so that's why my residual is 27. Okay, again, I would take each one of my students minus my predicted value to get my residual. Go ahead and pause your video at this point and see if we can figure out what our residuals are for all the other points. All right, so here are our residuals. You can tell that some are positive, some are negative. So if we were to plot this on a residual plot, we would have some dots that are above the line, some dots are below the line. So step 3 says plot the residual for each x value. So I've already gone ahead and I did that for you, okay? So this one on the left-hand side, this would be if we took all of those plots and all the points and we put them on a graph and we drew our line of best fit, okay? This is what our residual looks like, okay? So first we have to talk about correlation. What kind of correlation does this have? Well, it's going downhill from left to right, so it's a negative correlation. And looking at where the dots are they close to the line or are they far away? They're close to the line. So this tells me it has a strong negative correlation. Okay, strong negative correlation. But looking at the residual plot, are these dots close to our x-axis? So are they as close to this as we can get? No. So this really is not a good fit. Okay, we would like all of our dots to be something like this, where they're like really, really, really close to our x-axis. But our points, unfortunately, are not. All right, the reason why I mention this is because sometimes it can be very misleading. I mean, this one looks misleading too, because here it looks like, oh, those dots are really close to the line. They're not really. When you actually look at how close they are, they're not super close to the line. And here's another example. This one in this scatter plot, it looks like all of our dots are in a straight line. Okay, so it looks like it has a linear relationship. But look at what happens when you actually do the residual plot. Do you see that curve? So that means that this actually is not a linear relationship. Okay, it has a different kind of relationship. And our points are really scattered and far apart, so it's not the best fit. So just be careful. That's why we look at residuals, because the residuals give us a closer look at the actual values and see whether they are linear or not and whether they are a good fit. All right. For example 4, we're going to talk more about interpolate and extrapolate, which are part of the vocabulary words we talked about last time. So the graphic shows regional air travel data recorded by a domestic airline company. How can you use the data to estimate the number of air miles people flew in 2003? If the trend in air travel continues, what is the reasonable estimate for the number of miles that people will fly in 2030? So this is the data that they give us. They tell us the years, and then they tell us how many miles that their passengers traveled in thousands, okay? What we want to do is first we want to calculate the line of best fit. So look at my little hint here. It says count years since 1975. So when you're going to put your numbers into your table, when we're talking about years, we typically don't like to put in the years as they are. So years since 1975 would be 0. Whoops, I don't want the highlighter, I want the pen. Okay, so 1975, I'm going to use 0. Well, how many years after 1975 is 1980? Well, that's 5 years. This would be 10 years, 20 years, 30 years, and so on. So those are the numbers that you are going to put into your data. Do not use the actual years, use these data. So this would be your X values, your years will be X, and then your miles traveled would be your Y. Go ahead and pause your video. I would like to see you put those into your calculator and calculate the line of best fit. Okay, if you did your line of best fit, you should have an answer that's similar to mine. This one I took a screenshot from the TI-83, but you should have gotten data that is very, very similar to this. So from our data we could say y equals, in this case, the A is our slope. They use different letters on the TI 84. 47.87x, and then my B is 1,345.04. Okay, so what this tells us is roughly for every year, people were traveling about 48 miles, or 48,000 miles. And then that this is the rough start point for year 0, which is 1975. Okay, so that's what you should have gotten for this one. Now we have to look at what other questions they ask us. So they ask us to find what is a reasonable prediction for 2030? Well, how many years is 2030 from 1975? So if I take my calculator and I take 2030 minus 1975, we're predicting 55 years. So as you can see, 55 years would be here between 2005 and 2010. That may not, did I not do this right? Let me double check. That is 5 years, 10 years, 15 years. Oh, that's what it is. Oh, I'm off by a little bit. Hopefully you guys caught that when you were putting them into your chart. 5, 10, 15. I skipped 15. 20, 25, 30, 35, and 40. So 50 years would be beyond this. That would be extrapolation, because we're talking about beyond our data, okay? So it's outside the data that we're given. So what we can do is, like I said, 2030 is 55 years after 1975. We can substitute that into our equation. So I can say 47.87 times 50 plus 1,345.04. And I can get a rough estimate. I think that they're going to travel roughly 3,738,000 miles. Because remember, we're talking about 1,000 miles. Okay, so that's what extrapolation and interpolate mean. Here, is the graph. If you were to graph that, okay, interpolation is using a model to estimate values that are within the range of your known values. So we knew from 1975 to 2003, so that was inside our data. Extrapolation is what we just talked about. We talked about 2030 being 55 years after 1975. That is outside of our range of known values, so that's extrapolation. Okay, think of it inside, interpolation. Outside, it's extra. Okay, our other vocabulary word is causation. Causation describes a relationship. A change in the one variable causes a change in the other variable. So here are some examples. Okay, so our first example I want to talk about is this one here. A student found a positive correlation between the number of hours of sleep that his classmates got before a test and their scores on their test. He can conclude that he will do well on the next test if he goes to bed early. So we see the correlation. It's a strong positive correlation. So we have to ask ourselves, does the hours of sleep affect or change your test score? Okay, well, given this data, yeah, the more sleep the people got, the higher the test score was. So we can say that is causation, that the number of hours of sleep a person got caused them to have a better test score, or have them have a better or worse test score. So that is causation. Now, is that the fact for every single time? No. I've known people who get 2 hours of sleep and can score high on their test. And I've had people who get 10 to 12 hours sleep and do poorly. But generally, with the trends, that would be true. All All right, here's another example. A lifeguard notices that the outside temperature rises with the number of people coming to beach when the number of people coming to the beach increases. Can she conclude that the change in temperature results in more people going to the beach? Okay, so as the temperature rises, we see that there are more people going to the beach. Does the temperature cause people to go to the beach? Yes, typically, the warmer the weather, the more people are going to want to go to the beach. Okay, the cooler the weather, less people are going to go to the beach. So that is another example of causation. The temperature has caused the result of the beachgoers. Now you have to be careful. Correlation does not imply causation. So sometimes something can have correlation and be correlated with each other, but it's not what it actually caused it. Okay, this boy here, it looks like, according to the mom who's frustrated with this remote in the TV, it looks like it's going to be that boy because he's the one that doesn't have a remote or a game controller in his hand. Okay, but does that mean that he's the one that threw it to the TV? No. Okay, it could have been this girl. Look how guilty she looks. Okay, so that causation and correlation sometimes go together, sometimes they don't. Here's another example. This was a study, a true study that came up and said ice cream sales is correlated with homicides in New York City. So does ice cream sales cause homicides? Homicides are murders? Do murders cause ice cream sales? No, not really. But if we look at it like this, warm weather caused those things. When the weather is warm, the ice cream sales increased. When the weather is warm, more people are out and about, and then the study showed that the murder rate was higher. So the warm weather is correlated to those things, but doesn't mean that these two things are correlated to each other. Okay, ice cream sales don't cause murder rates don't cause ice cream sales. So correlation and causation can be very different. All right, at this point, we're going to do formative number 2. Most of the things that are on the formative are from when we talked about the last lesson. There is maybe 1 or 2 questions that talk about residual plots. Please use your graphing calculator. You can use your notes if you would like to. Show all work when you can. Please make sure you're demonstrating academic honesty and doing your own work. And of course, try your best. I am available in our virtual classroom if you have questions or you want me to check something for you. Feel free to stop by.